Welcome to lecture number 13 of graph theory. Today we will consider a new topic, namely graph coloring. There are two types of colorings that we will consider: the vertex coloring and edge coloring. First we will deal with vertex coloring and then go to edge coloring. To introduce the problem, let us consider this following question. So, suppose there are some committees. So, we will say the members of the committee. So, that is it is a set, right. So, we can say, so person number 1, 2, 3 belongs to a committee, and say 2, 4, 5 belongs to another committee, say 4 and 6 form another committee, 8, 9, 10 forms another committee, and 2, 8, 10 forms another committee, like this. Now, these committees meet. When a committee meets, it takes about 1 day to finish, full day meeting. So, we have to schedule the meetings of all these committees, but the problem is that some committees have contain the same person. For instance, this committee 1, 2, 3 and 2, 8, 10 have 2 in common. So, therefore, the day this first committee meets, this committee, these two committees cannot meet on the same day. This committee and this committee cannot meet on the same day. So, they have to meet on different days. So, the question is, how many days are required? So, how will you solve this problem? So, first we would like to convert to a graph theory problem. So, the question is, so for instance, why can't two committees meet on the same day? It is because there is a common person. Therefore, we will consider each of this committee as a vertex of a graph, and then if there is any common member in the committee, we will put an edge between the corresponding. So, this is a vertex now, this is a vertex now, we will put an edge between them. So, then between this and this there is an edge, between this and this there is an edge, between this and this there is an edge, and between this and this there is an edge, and let us see 4, 6, now there is nothing common here. So, therefore, this is the edges. So, which means that whenever there is an edge between two vertices, the committees corresponding to those two vertices cannot meet on the same day. So, now we will find out the committees which can meet on the same day. For instance, this committee, right, and this committee can meet on the same day because there is no edge between them. And is there any other committee which can meet on the same day? Yes, this also. Right, this also can meet on the same day because they do not share anybody common. Now, this cannot meet on the same day, this also not. Okay, so now we have to use another day. So, this red correspond to the first day, and another day to schedule this meeting, and then same day this cannot happen. So, we need a third day for this meeting, right. So, here I used some colors to find the red color indicates the first day, the green color indicates the second day, and this violet color indicates the third day. So, this 3 colors correspond to 3 days. So, we need 3 days to finish this meeting, finish all these meetings, to schedule all the meetings, because so this correspond to this graph coloring problem. Here we were looking for the minimum number of colors which correspond to the number of days required, so that the colors are given to the vertices of the graph, such that whenever there is an edge between the two vertices, we should not have any they should not get any the same color, right. This is the kind of thing. So, here the graph coloring graph, we could have drawn the graph more neatly like this, right. This is our graph. So this is the graph. The vertices correspond to the committees, and the colors will correspond to the vertices. Here one, this is the coloring problem. The red color is given. If you look at the red colored vertices, they form an independent set. That means there is no edge between them, and so here this is the coloring, and then here we have a violet color. So therefore so let's formally define the graph coloring problem. A vertex coloring of a graph G equal to V comma E is a map, it's a function C from V into S, S being the available colors, such that C of V not equal to C of W whenever V and W are adjacent, right. So let elements of the set S are called be called the available colors. The smallest integer k such that G can have a k coloring, right. That is a vertex coloring from V to 1 to k is called a the chromatic number chi of G of the graph. This is the formal definition of this. In other words, we are supposed to color the vertices of the graph in such a way that whenever there is an edge, they should get different colors, and the number of colors should be minimized. We can look at some examples and try to understand the coloring problem again. So for instance, let us take our favorite examples, the complete graph, the complete graph Kn. So this minimum number of colors that we will use will be called the chromatic number. The notation is chi. So we are interested in chi of Kn. What will be the minimum number of colors? So it's very easy to see that it has to be n, because you cannot share any color, because any two vertices, if you consider, they should get different colors in the complete graph, because there is always an edge between them. So therefore they should have they should get n colors. Now what about a complete bipartite graph KNN? This also has lots of edges, but still it happens that it requires only two colors. Why is it so? Why does it require only two colors? Because so there's a complete bipartite graph is like this in vertices, and then we have all the connections between them. So all the connections between the two sides. So this side can be given, say, white color, and this can be white color, and this can be given black color. Okay, so this is the complete bipartite graph. So two colors are enough. And now we can look at some other cases. So what about trees? So for instance, let's look at this tree. How many colors are required to color the tree? So some thought will reveal that only two colors are required, because you can color it red and you can color it green here, right. Then you can color it red layer by layer, right. Then you can color it green here like that, right. So two colorable. This requires only two colors. And what about cycle? So this is a cycle, right. So cycle, whenever you say cycle, even and odd cycle matters. This is an even cycle. So how many colors are required? As a little consideration will reveal that only two colors are required. So we can give this colors black, right, and the other color, say, we can give white, sorry, okay, red we can give. So with using two colors we can color this one, right. And what about an odd cycle? Odd cycle may be like this, or So you can try to color like this, like I did in the last case. So this one, this one, and this one, this one. So here I have a conflict because I have green here, then it's a black here, green here, black here, green here, black here. Here what will I do? Here I cannot give green, I cannot give black. So I will have to use a new color, right? So you can see that it requires 3 colors. Chi of Cn equal to 3 when n is an odd number, right? The if it's an odd length cycle, then we need 3 colors. So between the odd cycles and even cycles, there is a difference. Odd cycle requires 3 colors, the even cycles require only 2 colors. So when you consider the couple of examples we considered, the even cycle and trees, so both of them required only 2 colors. They are if you remember what the definition of the bipartite graph, both of them are bipartite graphs. So in fact that is why both of them, why are both of them bipartite graph? Because the tree is like this. So you can consider the first root of the tree here, the immediate neighbors on the other side, and then the immediate neighbors of that on this side, and like that, right? So tree is a bipartite graph. So similarly even cycle is a bipartite graph because we can always draw this cycle like this, isn't it? The even cycle can be considered like this. So this is so these are both of them bipartite graphs. So it's not surprising that they required only 2 colors. Why is it so? Because if you take any bipartite graph, so it will look like this, 2 parts, and the edges are always going from one side to the other. So the here it is like you can use one color for this side and the other color for this thing, because the edges are always from one side to the other. So it so happens that all bipartite graphs are 2 color, so essentially 2 parts. So it's not very surprising, because if you look at the coloring question carefully, it so happens that when you look at a color class, a color class means the vertices which got the same color, they should form an independent set in the graph, isn't it? Because there is no edge between 2 vertices of the same color. So it's like we are trying to cover the graph with independent sets, right? Each color corresponds to an independent set, another color corresponds to another independence. Like that, we just have to put every vertex in one of the classes, so that we are covering all the vertices with independent sets. So sets, what is the minimum number of independent sets required to cover the vertex sets, vertex set? That is what we are interested in. In a bipartite case, it is clear that you have 2 independent sets, and then it cover the entire graph. So in a clique, we have only independent sets of size 1, therefore we need n of them. So this will give rise to this thing. So if n is the number of vertices, chi of g has to be greater than or equal to n by alpha of g, right? So okay, maybe yeah, chi of g has to be greater than or equal to n by alpha of g. Why? Because each color class can contain only a maximum of alpha of g vertices. So one color class contains only alpha of g, but there are n vertices. So we should get right, at least so many colors, right? There should be at least so many colors. That is that's what we can tell about the relation between independent sets and the chromatic number and the number of vertices in the graph. Now the so you can all okay, of course you can take some little more complicated examples, right? For instance, if there is a wheel, how many colors are required? Okay, so it depends on how many colors are required. This will always require a new color. For instance, here one, this is green, so we may use this one, and we may use this color, and then we may use this color, and we may use this color here. This is, and then we will have to give a new color. So this color is not possible, or neither red color is not possible. So we may have to use a different color for the middle vertex. So and so like that we can consider several examples. So another examples you may want to consider is the Peterson graph. How many, what is the chromatic number of Peterson graph? This is the graph, right? So how many colors are required to color this thing? So I'll leave it to you to figure out how many colors are required for this graph. And now let's look at, suppose we want to come up with an algorithm to color the graphs. So not necessarily optimum, some coloring is required. So we want some method to come up with the coloring. What should be the easy and very straightforward strategy to come up with a coloring for a given graph? So this okay, so this is like this, and okay, before that let's consider another question. So what about the number of edges? For instance, can I say that if the chromatic number of a graph is k, if chi of g equal to k, then can I somehow say that the number of edges m in the, so number of edges m in the graph is greater than or equal to some function of k? Is it possible? So what we can show is that m will always be greater than or equal to k into k minus 1 by 2. If k is the chromatic number, there should be at least k into k minus 1 by this k choose to edges in the graph. Why is it so? Because if you consider the color classes, so these are independent sets, right? The color classes, there are k color classes. There are k colors, the first color class, second color class. So there are k color classes. Between any two color class I and j, there should be at least one edge. Why is it so? Suppose this edge was not there. Suppose there should be at least one edge between any two color class. At least one edge, maybe more. Suppose is it possible that there is no edge between these things? Then I would say you merge these two color classes. Merge these two color classes, and you can make it a new color class together, because anyway there is no edge between them. Why do you want to give two different colors to the vertices of this and this? So therefore what we infer is between any two color class there is an edge. There are k color classes, therefore k choose 2 edges should be there. K choose 2 because there are k choose 2 pairs of colors. So that is k into k minus 1 by 2. So this will be a lower bound for the number of edges. This is what I am saying k into k minus 1 by 2. Okay, good. So next question I am considering is, how do we come up with a coloring for the graph? What would be an easy way to color the graph? So suppose let us take this graph. Maybe we were looking at the Peterson graph, or maybe this graph. So I am just drawing a graph. So I want to color this graph. So one strategy I may want to adopt is to give a color for an arbitrary vertex, and then I take another vertex, say I took this vertex, and I see that this is already colored, then I can give a different color to this. Now I take this vertex, I see that these two colors are already used. Now I may want to use a new color for this. So when I go here, I see that this black color and blue color is used, but green color is available. So I can use the green color. Whenever I see a new vertex, what I do is I look at its neighbors which are already colored, and I try to reuse a color if there is anything available. If all the colors which are up to now used is there in the neighborhood, then we cannot reuse any color, we have to use a new color. This is the way we keep going. Here we can use the black color, so here we can use the green color, here we can use the blue color again, right. Here you can use the green color once again. So this is the strategy of coloring. So one question that comes to your mind is, why is this an optimum coloring? So in this case it looks like it is an optimum coloring. The three colors are required here. Why? Because if you take a triangle here, this requires all the three colors, right, because you cannot repeat the colors here anyway. So therefore in this case it is an optimum coloring, but in all cases it need not be an optimum coloring. So some cases it may so happen that we end up using too much. So therefore but still we can try to come up with some kind of an upper bound to like saying that okay, whatever it is may not be optimum, but we have only used this many colors. So what kind of upper bound is possible? So the easiest way to get an upper bound is to note that whenever I consider one new vertex for coloring, what it does is it looks at its neighbors which are already colored, but how many neighbors can it have maximum? It can have only maximum of delta neighbors, delta being the maximum degree, right, delta neighbors on it can have. So therefore in whatever way we can see only at most delta colors on its neighbors. So it may now it will use a new color. For instance, it is possible that it may use a new color. So delta plus 1 colors it will use anytime, because otherwise, so in another case if you see delta neighbors, so this delta plus 1 color is already there in the graph, it already given to some vertex in the graph, we can reuse that color, there will not be any conflict. So therefore it so happens that you can color the graph in most delta plus 1 colors, at most delta plus 1 colors. It's it won't be possible. I mean it will there won't be any situation where you will have to use more than delta plus 1 colors. But again this, if you carefully look at it, it may come to your mind that maybe it is a little too much. So you may not use delta plus 1 colors in any situation. So is there any particular situation when you really use delta plus 1 colors, a tight situation, tight example, like where you have to use delta plus 1 colors? So one such example is the complete graph. For instance, if you consider a Kn complete graph on n vertices, what is delta? Delta equal to n minus 1. So now how many colors are required? Delta plus 1 colors are required, is equal to n colors are required. So you cannot avoid the situation here, because if you start doing what, however you try, you will end up using delta plus 1 colors, right. So there are situations where you need delta plus 1 colors. So can you quickly think of another example where delta plus 1 colors are required? So one such example is this. So say an odd cycle, right, a cycle with odd number of vertices, 3 plus 3 plus say 7 cycle, odd number of cycles. How many colors are required? Delta equal to 2 here, maximum degree is 2. The number of colors required is delta plus 1 equal to 3. So, this is also one such situation where delta plus 1 colors are required. So, the odd cycle and complete graphs are some examples where we will need delta plus 1 colors, but then so are there some other situations? Of course, you can think of some situations where there is a graph with several connected components and one complete graph, one kn in it. In that case, so for instance, if this happens to be the component with the largest chromatic number among its components, so we can independently color these things, you can reuse the color among these things. But suppose here is where I take the maximum number of colors to color, then it will happen that here maximum degree also is here, suppose. So, then it may okay, in fact I want to say that if the maximum degree comes from this component, then that is delta equal to n minus 1. Then here, because of this clique here, we have to give delta plus 1 colors, right. So, this is similarly one of the components can be an odd cycle. So, let us forget this kind of situation. Let us say that we are only interested in connected graphs, because if there are several connected components, so each connected component can be colored separately without worrying about the other part. So, therefore, we will just say that the odd cycles and complete graphs are examples where you need delta plus 1 colors when we consider only connected components. Now, we are going to study an interesting theorem where and this theorem states that the number of colors required is in fact at most delta for all other cases. That is interesting enough, isn't it? So, the only connected graph which require delta plus 1 color is the complete graph and the odd cycles. So, now our question is here this is the statement we are going to look at next. Let G be a connected graph, and if G is neither complete nor an odd cycle, then chi of G is less than equal to delta of G. So, so we will look at the proof of this thing. This theorem is called Brooks theorem, and we will study that, right. Now, to come to the proof of Brooks theorem, let us do an induction. So, we will assume that for all small graphs the statement is true. So, when I say small graphs, so for one vertex graph it is definitely true, for two vertex graphs, so you can always check, 3 vertex graphs also you can check. So, let us assume that for smaller graphs it is true. For on smaller graph means on smaller number of vertices the theorem is true. Now, we will assume that we are considering a graph on n vertices, right. Now, we consider some vertex, right, and now we look at its the graph after removing that, right. So, it has its neighbors, these are its neighbors. So, of course, this graph having only n vertices can be colored with delta colors. Now, one thing we should first notice is that the degree of this vertex is delta, because if it is not delta, suppose it is only delta minus 1 neighbors it has. So, how many colors it will see here? For instance, this is colored by induction hypothesis, it can be colored using delta colors or delta plus 1 colors, depending on whether it is complete graph or odd cycle, this may be right, but whatever it is. So, as far as the original graph is concerned, if this was not a delta degree vertex, it will see only delta minus 1 colors here, and so it can be colored using so many delta colors, right. Or we can in fact argue that any graph which violates the statement, that means which requires delta plus 1 colors, should have to be a regular graph on with the delta vertices. Why is it so? Because the earlier strategy we considered, we were in fact finding a certain kind of ordering, right. We just found out a vertex and then we found out another vertex, and we gave a color to this thing and we found out another vertex, and then we looked at the neighbors of this, right, and decided to color this based on whatever colors we have already given to the neighbors, right. So, when we do this procedure, we notice that all the time when I pick up a new vertex, I will be seeing only at most delta neighbors, therefore, the delta plus 1 color is available for this vertex. But then if I was doing it carefully, what I would do is I would try to order the vertices in such a way that every time I select a new vertex, I will pick up the vertices in that order, and in such a way that the number of colored vertices it has, I mean it is already considered vertices it has, neighbors it has already considered neighbors it has, is minimized, right. So, of course, I will be trying to pick up an ordering in such a way that every time I consider say vertex I, Vi, the ith vertex, the number of neighbors of Vi which is numbered lesser than I is as small as possible. So, for instance, if there was a vertex of degree delta minus 1 in the graph, right. So, I can always keep that vertex as the nth vertex, because anyway it is going to see only delta minus 1 neighbors in its neighborhood, right. Therefore, its neighbors with lower number will be at most delta minus 1. Now, once you remove this vertex, so there will be at least one vertex touching it. So, therefore, its degree will reduce. So, we can pick up that vertex, because that is another delta minus 1 degree vertex in the induced subgraph after removing Vn, that we can consider as Vn minus 1, and after that, so I can remove that vertex. Now, I can get a vertex with a lower degree. So, of course, so that degree is delta minus 1, I can pick up. So, every time I will be seeing only delta minus, you can see in this order, if the reverse order is this thing Vn, Vn minus 1, Vn minus 2, I can write down the things. Now, if you start eliminating vertices starting from V1 onwards, it is very clear that every vertex Vi will be seeing only at most delta minus 1 neighbors in the neighborhood of it, delta minus 1 neighbors in the neighborhood of Vi. So, therefore, we need only delta minus 1 plus 1 color, is it is equal to delta color. So, this was possible because we assumed that there was a vertex of degree delta minus 1 in the delta minus 1 or less in the graph. That is why we could do that, right. And now the okay, so now coming back to the proof of Brooks theorem. So we can assume that if our graph G needs delta color somehow, right. So by contradiction, let's assume that the n node graph G requires delta colors. In that case, it will be a regular graph, right. Otherwise it will need only delta plus delta colors, because if it need delta plus 1 colors, it has to be a regular graph. Now we removed a vertex. So this vertex V has delta neighbors here, and of course there is a coloring of this here. So now is it possible that this is a complete graph here? This is a complete graph. Now if this is a complete graph, now you can see that the degree of this vertex, all these vertices here will have same degree in the complete graph. So now we have delta plus 1 coloring for this, right. Now you can see that this also has, so essentially because this vertex is connected to this degree will have to go one more. So essentially it's a delta coloring for this thing, right. This is a delta coloring for the original graph will have degree delta, and the maximum degree of this complete graph will be 1 less, right. Otherwise there won't be, so this itself will be a complete graph, and we don't have to prove anything. So it will so happen that, so we can assume that this subgraph has a delta coloring. This has a delta coloring. Now we look at the colors on this, and if the colors are all distinct, then only we have problem, because if there any color is repeating, then there are only delta neighbors. If one color is missing, only delta, at most delta minus 1 colors are used on the neighbors. So we can use the next color, deltath color, on for V, right. So therefore we can use the deltath color for V. Now it so happens that so see, one thing we have to consider, so we have to carefully consider. So is it possible that this is somehow a disconnected graph? For instance, when I remove this, we are talking about connected graph. When I remove the vertex V, so its neighbors go into disconnected components. Is it possible? It is it's possible that this vertex V is connecting these parts together. It's connecting these parts together, right? But it's in that case, what we can do is we will, because these two are disconnected parts. So these colors, if at all there is a color here, green color here, so I can try to change the color on this thing with a green color. For instance, the only problem, as I mentioned, this is all the colors are different. I can try to get a common color here between this and this, because within this component I can exchange colors. So rename the colors. I can make the green color red and red color green. So that so because these are totally different colors from this, right? These colors are different, these colors are different. I can, whatever color comes here, I can rename with the name, the color which is available here, which will make a repetition of colors on the neighborhood, and therefore it will so happen that there is a repetition of colors. And since there are only delta neighbors, so, and we are using only less than delta colors, so we can use the deltath color for this vertex, Now the next point. Okay, so now, so what I have argued now is, if you consider any vertex V, essentially this will be one component and there will be several components, all the neighbors are going to this component, and again the colors on the neighbors are different, so I can just use some different colors to show that different colors. So this violet, yellow, green and red I can show like this, and right. Okay, now what I can do is to consider, say here I have green and red color, right? So I can try to study the components involving green and red colors alone. So there are many other colors, yellow, violet, all these things are there, but then I look at the subgraph of vertices induced on green and red colored vertices alone. So see, that will form some connected components, right? For instance, it may be like this, right? So of course it won't be like this, it will be, yeah. So essentially I am trying to locate the green and red components, so that will form some connected components, right? So now I can look at those green and red connected components and then ask this vertex and this vertex, for instance I will draw it like this. So this is V, this is its red neighbor and this is its green neighbor. So now I am only interested in the green and red colored vertices of the remaining graph, because by induction we could color this remaining graph, and now there will be a connected component of green and red here which involves this. There will be a connected component of green and red which involves here. There will be red vertices, green vertices. Yeah, this will be just red and green. Okay, all this, some connections will be there between them. Okay, so now similarly there will be green and red here also. So is it possible that these two connected components are different, or will they be same? So at first look it may look like they can be different or same, whatever, but then suppose they are different. If they are different, then what we can do is, in this connected component I will rename the red and green. For instance, I can make all red green, red vertices green here and all green vertices red. It won't affect anything, but the coloring will be still valid. Why is it so? Because if you take any other vertices, outside vertices, they may all have some different colors only, right? So they, whether it's seeing, so for instance they are neighbors, for instance whether it is yellow or violet or something, whether in the neighborhood they see green or red doesn't matter to them, it has to be different, right? So but then if I change the color of this red to green, the only vertex for which it matters is a neighbor which has already got a green color, but then that I am making to red, right? So I am consistently doing it in the entire component, therefore it won't be a problem, it will be still a proper coloring. So if this component is disjoint from this component, is there is no path starting from here to here, then here I can keep the initial coloring, and here I can convert all the red to green and green to red, which will essentially make a green vertex here, right? Because red will become green. So now what does this vertex see? Two green vertices on its neighborhood. If it sees two green vertices on its neighborhood, its meaning is that so it is the maximum, the number of colors it sees on its neighborhood is at most delta minus 1 or less, right? At most delta minus 1. So we have one more color, we can use that color to this. So from which we can what we can conclude is we cannot do this thing. So because of some reason. What is the reason? Because the reason is when you try to exchange the green color to red and red color to green, that process will should go to the entire component. So here everywhere it will get exchanged, and this will become this green will become red, and while this red became green and this green become red, so there won't be anything good, right? Because there was a red green before, it will become a green red, so there won't be any difference. So it will so happen that the number of colors the vertex sees on its neighborhood remains the same. The entire set of delta colors are seen on that. So we can assume that this should happen, otherwise we will solve the problem here itself, right? Because there will be a delta coloring. So that assumption that it could not be colored using delta colors will be wrong. So what we can say is that, so these two components are same. In other words, if I take the vertex v, right, and look at its red neighbor and green neighbor, and the connected component between, this is green neighbor, the connected component of red and green vertices between them, it should be that so this should be the situation. That means your red and green connection should come together, right? This should be they both these neighbors should be contained in the same connected component of red and green component. Now we are interested in how this connected component will look like. So now will it be this complicated, some complicated structure like this? So if you look at this carefully, so is it possible to have two green neighbor for, as I drew here, is it possible to have two green neighbor to this red vertex? So if it has two green neighbor, so how many, so for as far as this vertex is concerned, how many neighbors in this graph it has? Because its maximum degree is delta only, so now one edge is towards this outside vertex, this v, right? So this u can only have at most delta minus 1 neighbors here, and if two of them has same color, only delta minus 2 colors will be used in its neighborhood. Only delta minus 1 neighbors are there in this in this subgraph, right? Now out of that, two of them are using the same color, that means only delta minus 2 colors are used. We have two extra colors, one of which is already there, red color on this. So we have one more, so we can say maybe it is some blue color. I could have reused that color, right, for this thing. So I'll reuse the blue color on this thing, and it will help me to use that blue color to for this thing, and then red color will be released, because red color will not be there in any of the other things, right? We haven't done anything here, so therefore the red color can be given to this vertex, isn't it? In other words, I release the red color from this vertex and given to this vertex. So we can do it that way. Okay, so that's what we can do. So what I conclude is, you cannot have this vertex u cannot have more than one green colored neighbor of it. So in other words, this is I can clearly say that this is not correct. So yeah, this picture is not correct. Eraser small. Okay, so this edge is not there, this cannot be there, right? So it can only have one green neighbor in this connected component. Now I will concentrate on this green neighbor and ask how many red neighbors it can have. So look, this is a red neighbor, right? Sorry, so this is now, this is a this is a red neighbor, this is a red neighbor, and here suppose it has two other red neighbors here, suppose. So this is already a red neighbor and there's two more red neighbors. So out of the delta neighbors this has, 3 of them are red, so which means only delta minus 2 colors are used, right? Total delta neighbors, out of that 3 are using the same color, so delta 2 colors are used around in its neighborhood. So that means 2 colors are free, but out of the 2 colors, one is already there, this one is the green color because it's already there here, so there should be one more color. So let's say this is blue, then we could have given blue here, right? So if it is okay, so if it is blue, then see, there is no problem, this gets disconnected from the rest of the red green thing, so I can safely change this to green. So this and this will become green, so now the red will be free for giving this, so red can be given to this now, right? The original thing. So therefore what I can infer is this this is red, this is green. This green cannot have 2 red neighbors, maximum 1 red neighbor. Other than this earlier one, it can have only 1 red neighbor. So I can sorry, what I can say is that this is not there, right? Only 1 red neighbor it has. Okay, so it can only have this, sorry, so this is, and then 1 red neighbor, and now the next red neighbor, so this is red, this is green, this red is coming in a path, and then here if you see this red, how many neighbors can it have other than this green? Can it have, it definitely it cannot have another red neighbor. Can it have more than 1 green neighbors? There is one I have done. Is it possible to have 1 more green neighbor, right? So it is because if you can have 1 more green, suppose you have 2 green neighbors, then the same thing can be told about this. There are delta neighbors of total delta neighbors for this red vertex. Out of that 3 are green, that means only delta minus 2 colors are used. There will be 1 free color other than the red, 1 more free color. So delta minus 2 on the neighborhood, 1 on itself, the delta minus 1 more will be, it can be, say, as usual, blue, suppose it is, then we could give blue to this instead of red. That will cut away this portion from this. So then what will I do? I will change the colors, exchange the color of this and this. So that means this will become green and this will become red, right? This will become green, this will become red. So essentially now you don't have to worry, because the next is a green neighbor. There is no red or green attached to this, so we can safely exchange this thing. Now this and this has become green, so red is free. The free red can be given to this outside vertex, so that will allow me to color the entire graph in delta color. Which what do I infer from all these things? It means that I cannot have I cannot have this extra green neighbor here, right? There is only one green neighbor. That's what it means. Okay, that's what it means. So so we can conclude like this, that that red green component will be so this is V. So if we consider the red green neighbor, so this is the green neighbor and this is the red neighbor, we will end up with a path rather than a any complicated structure. So this will be like this, in fact. So this will be green, this will be red, and this will be green. So it will be rather a path. So this is red, sorry, and this will be red, like this, right? So and so between we can whatever we did between any the arguments that we did for red neighbor and green neighbor can be repeated for any two colors. So which means that if you pick up two colors in the neighborhood, between those two colors I will always get a red so that the path, rather that a component of the two colors involving these two vertices has to be always a path rather than any complicated structure. So from the rest of the proof will be considered in the next class. Thank you.